Well, here we are at chapter 19, and this is the introductory first video cast. To be successful in this video cast, you need to have 4 things out. First of all, find some paper. Second, find a pencil or a pen. Third, find a periodic table, preferably a crappy one. Fourthly, it helps to have your book because you can follow along, and I'll show you some pictures as we go too. So don't be afraid to pause along the way, read a little bit of the book, then come back and look at this. This video cast is more conceptual than some of the other ones, and then following this there'll be a lot of sample problems. So first focus of this is to answer the question, where have we been? Where have we been in this class? And where are we going? Where have we been? Where are we going? In AP Chemistry, a lot of teachers will tell you that there's the big 4. The big 4 things that are always tested. First one of the big 4 that you encountered was in chapter 14 when we talked about kinetics. Kinetics had to do with the speed of a process, or the speed of a reaction and the mechanism and how it worked. This happened in chapter 14 of Brown-Lemay-Burston. We're not looking at that in chapter 19. That was chapter 14. Second big of the big 4 was equilibrium. And this was 3 monster chapters that we just completed. Had to do with the reversibility of a reaction, had to do with acid-base equilibria, solubility equilibria. And this was chapters 15, 16, and 17 in Brown-Lemay-Burston. Lots and lots of big stuff. You can probably see why they call it one of the big 4. The next one is this chapter. And it actually partners with chapter 5 as well, because this chapter is entitled Thermodynamics. And we actually looked at a good chunk of thermodynamics back in chapter 5 when we learned what delta H was. Delta H was called enthalpy, and it was the heat of a reaction at constant pressure. And remember, if it was negative, it meant that energy was given off from the system to the surrounding, and if it was positive, it was enthalpy, was energy that was taken in. Well, in this chapter, chapter 19, which is the third of the big 4 now, we learned 2 new letters. Besides delta H, we encountered 2 new ones, S and G. And these 2 new letters, partner with H, help us answer a really huge question. Not how fast, not if a reaction is reversible and where it sits, but it answers the fundamental question of, does a reaction happen or not? Does a reaction happen or not? If or if not, a reaction will happen. The fourth of the big 4 is called electrochemistry, and this you'll encounter in our next chapter, chapter 20, and that has to do with lots of oxidation and reduction. So this is where we've been. Chapter 19 and 20 in Brown-Lemay-Burston is where we're going. And we're going to answer the question in this chapter, will a reaction happen, or will a process happen or not? Will a process happen or not? And we can focus on small things for processes that might seem like really simple. Like, for example, this pencil that I have, if I let it go, will it fall to the table? And the answer is yes, it will happen by itself. This is a process that just naturally happens. Why does it happen? Well, there's lots of science behind that. We've got the attraction due to lots and lots of mass of the Earth. It's called gravity that accelerates it. And we can go into that really deep. But in chemistry, we look at a process like the freezing of water. Does that happen by itself? Well, that is what chapter 19 is going to answer for us. We've got to use a fancy word for this process happening or not. And the fancy word in chapter 19 that we'll use a lot is the word spontaneous or spontaneity. If something happens by itself without outside intervention, it is said to be spontaneous. And in the front picture of your chapter 19 book, there's a picture right here of a gas burner on a stove. And as they say, the combustion of natural gas, which is composed mostly of methane, producing carbon dioxide and water is a spontaneous process. Once lit, the natural gas burns spontaneously. The reverse of the reaction, the combination of carbon dioxide and water to form methane and oxygen, does not occur spontaneously, though. And so we'd say it's non-spontaneous. This is an example of a chemical thermodynamic process that is spontaneous in the forward direction. And some people jump up and down right now and get all bent out of shape because they say, yeah, but if I have a bunch of methane gas, it doesn't just light on fire. You got to do something to get it to light on fire. And now we got to back up here to where we've been. Remember in chapter 14, we talked about the mechanism of a chemical reaction, and we said that to initiate a chemical reaction, to get it started, many times we needed a little bit of energy called an activation energy. That's not what we're looking at in chapter 19 here. We're saying the activation energy has been added, and now the reaction is proceeding. Will it, once it gets the activation energy, occur spontaneously, or will it be non-spontaneous and not occur? So careful of the mixture between where we've been and where we're going. Careful, because chapter 19 does not answer the question, how fast will the reaction happen? Or how fast will this process happen? But it simply answers the question, will the process happen or not? Will the process happen or not? So if you need to, pause the video now because we're almost done with the first page of notes, and make sure that you've got all of these written down on a piece of paper. Let's back up just a second. In chapter 5, we learned a little bit about thermochemistry, and we learned this letter right here, a triangle H, also known as enthalpy. And enthalpy, we said, was the heat at constant pressure of a process or a reaction. And we pretty much looked at also that and found out that things with big negative delta H's, like for example explosions or things that combusted and burned, they were spontaneous. They occurred naturally by themselves. We didn't focus on this in chapter 5, but it's one thing that I remember talking about with several people, that hey, things that are really negative delta H's, they happen by themselves. But then we looked at some other things with small delta H's, small negative delta H's, or maybe positive delta H's, and we found out that those things also occur spontaneously. Like, for example, freezing of water at 20 degrees Fahrenheit. Hey, that happens spontaneously, but energy is released. Energy is taken in, and so it's an endothermic process, but it happens spontaneously. So something else must partner with delta H to drive and determine spontaneity in a process. Remember what spontaneity means, and I'm going to use that in a word tons and tons of times during this chapter. It means it will occur by itself without outside intervention. It's a process that just naturally happens. Something else must partner with delta H, and in this chapter we'll look at those something else's along with enthalpy. This something else is known as entropy, E-N-T-R-O-P-Y, and is symbolized by the letter S. Symbolized by the letter S because it helps us determine if something is spontaneous or not. Entropy alone does not determine if something is spontaneous, just like enthalpy, delta H, does not determine if something is spontaneous or not. These two critters combined with one another will answer the question, will a reaction occur by itself or not? And that's the whole focus of this chapter 19. Delta S actually is a numerical value that we can calculate. And as a kind of a slang, not perfect, but pretty good definition, entropy, S, is a measurement of the randomness or the disorder of a system, the mixed-upness of a system. And we'll actually take a closer look at it in the next video cast where I do some sample problems, and we'll talk about how the randomness or disorder of a system actually determines or is determined by what's called the microstates that the atoms or molecules that make up a system can occupy. And this actually has to do with the statistical ability of different molecules to vibrate, translate, or rotate in the way that they're existing at that time, gas, liquid, or solid. Ludwig von Boltzmann actually was one of the first to study this, a super duper famous scientist. Was one of the first people to talk about entropy in his equation that contains what's known as the Boltzmann's constant, this K right here. It calculated how many microstates a particular substance could or were associated with it. So backing up once again, a simple slang way to talk about entropy is to say, hey, how random or how disorganized is a particular system in terms of mixed upness. And you can think of it kind of this way too. Here's an easy way to think of it. Solids, liquids, and gases. If you remember when we studied these changes in states of matter, solids are usually very organized and arranged. Liquids start to become a little less arranged and have a little more randomness or disorder, and therefore would have a little more entropy. And then gases, of course, have a lot of randomness and disorder because they're even more spread out, and so they would have possess a larger amount of entropy. And we're going to actually numerically calculate that as well, but this is a good qualitative way to think about it too. Like enthalpy, delta H, we look at entropy, delta S, as a change, And remember this triangle right here, and also right here represents the word change. So we look at the change in enthalpy or the change in entropy. And be careful, these two words look alike and kind of sound alike. So don't confuse them, and repeat them in your brain 4 or 5 times right now. Pause the video and say them out loud 6 or 7 times right now. Make sure that you know that enthalpy has to do with heat at constant pressure of a system, and entropy has to do with the randomness or disorder or mixed upness of the system. To calculate the entropy change of a system, we do the same thing that we did with the enthalpy. We take the final entropy of a system and subtract from it the initial entropy of a system. If entropy happens to be need to be calculated at a constant temperature, or this is in a process that is known as isothermal at one constant temperature, iso meaning one, thermal meaning like thermodynamics at one constant temperature, then we can use this equation. This is a really cool equation that allows us to calculate the change in entropy of a system as related to its heat, its reversible heat. And remember, if it's at constant pressure, you can actually substitute delta H right here, the enthalpy divided by its Kelvin temperature. This is really handy, actually, to calculate the entropy change at a phase interface, or when a substance is going from a solid to a liquid, or a liquid to a gas, or a solid to a gas, or vice versa in any of those areas. For phase changes, remember the temperature does not change. For example, at 273 Kelvin, which is 0 Celsius, at standard atmospheric pressure, water will go from a liquid to a solid, or from a solid to a liquid. And so this value would go in here for the temperature, and then we would look at its enthalpy change, which is known as the enthalpy of fusion when it's changing from a solid to a liquid. I'll do a sample problem of this in the next video cast, but it's talked about really well on page 8 in your textbook if you're following along in the 10th edition. So if you're calculating this, you should note that enthalpy has units. Entropy has units. Just like enthalpy has units of kilojoules per mole, entropy also has units. And you can see those units right up here by this calculation. This is a measurement of energy right here, usually measured in joules or kilojoules. And this is a measurement of temperature right here, measured in Kelvin. And it must be the absolute Kelvin temperature scale. It can't be Celsius. And so if we look at this equation, heat divided by temperature, I said that heat energy is usually measured in joules, and temperature usually measured, or it has to be in this case, on the absolute temperature scale known as kelvins. And so entropy is almost always measured in joules per Kelvin. Joules per Kelvin. So notice that entropy is measured in joules per Kelvin, whereas delta H is usually measured in kilojoules per mole, or simply in kilojoules, depending on what you're looking at. Notice the difference. This is usually measured in kilo. This is usually measured in just straight joules. And we'll find out when we look in the back of the book at lots of tables of enthalpy and entropy that enthalpy is always given in kilojoules and entropy is always given in joules. So now that we know the two things, enthalpy and entropy, that help answer the overall question of the chapter, remember the overall question was, will a reaction happen or not? Is a reaction spontaneous or not? And the two things that cover that are enthalpy and entropy. We can look back at what are called the laws of thermodynamics. We learned the first law of thermodynamics back in chapter 5. That first law said that energy is conserved, that energy lost by a system is gained by the surroundings. Or, if energy is lost from one thing, it's transferred to another. And in a perfect world, if energy is lost by one thing, it's completely transferred to another, but usually we lose some to the surroundings as well. Well, there's a second law, and remember this law had to do with delta H. There's a second law of thermodynamics, and since this one had to do with delta H, you can probably guess what letter the second law has to do with. It has to do with S, or delta S. And on page 811 in this 10th edition of Brownlow-May-Burston, it talks about how the second law of thermodynamics says that entropy, remember entropy is the randomness or disorder of a process, increases for any irreversible process. And for any reversible process, thing that can go back or forward, the entropy is equal to 0. In other words, entropy is always increasing. Disorder is always increasing in the universe. And you can use this as a simple process of looking at your room in your house. Does it spontaneously clean itself and get neater and look nicer? Well, I mean, if you know about that, let me know, because I need that to happen in my house. No, of course, it continues to get dirtier and messier, but you have to put some energy into it to go and make it cleaner or make it nicer. So some good reading about this. This is a real short little essay, actually, written by a really famous scientist author named Isaac Asimov. Is a short story that he wrote called The Last Question. This is actually linked for you on our website. Underneath references off the site on our very home page. And it's about halfway down or so. And it says, Isaac Asimov, The Last Question, Entropy. And the cool thing about this is a story he wrote back in the 1950s. And don't roll your eyes. I know it's over 50 years old almost now, or for sure now. But he predicted back then some things that computers would be able to do that we're still hoping to do today. And he takes the computer and spreads us out for thousands of years with what they'll be able to do. So take a look at that, and if you're at all interested in the future of science and what it'll allow us to do, take a look at Asimov's The Last Question. It's a quick read, and it actually goes right along with this chapter. In our next video cast, we'll get to some mathematical examples and some qualitative examples that have to do with entropy, and enthalpy as well. And then we'll get back to another video cast like this that talks a little more qualitatively about it as well. So good luck with the next video cast about thermodynamics, enthalpy, and entropy, and the calculations that are associated with it.